Hello students. So I hope you all are doing good. Today we are going to start Electromagnetic Induction NCERT Exemplar. So this is the disclaimer. Learning objectives. After this lecture you will be able to understand magnetic flux calculation through different geometrical shapes, squares, loops in various magnetic fields configuration. You will be able to comprehend the factors affecting self-inductance in solenoids, particularly the relationship between length, cross-sectional area and number of turns. Learn the principles of electromagnetic induction and conditions under which EMF is induced in coils, time-varying fields, motion in magnetic fields. And you will be able to apply mathematical concepts to solve problems involving time-varying magnetic fields and induced currents in the coils, solenoids. So there are total 32 NCERT exemplar questions in chapter electromagnetic induction, and in this chapter, in this lecture, we are going to do some of these questions in our today's lecture. So let's begin. So first question, NCERT exemplar 6.1. So question is, a square of side L meters lies in the XY plane in a region where magnetic field is given by B equal to B naught 2I cap plus 3j cap plus 4k cap Tesla, where B naught is constant. The magnitude of flux passing through the square. Okay, so magnetic field is given in the vector form. Okay, in the form of unit vectors. I is the unit vector of x axis, j is the unit vector of y axis, and k is the unit vector of z axis. So B is given in the vector form, and square is of side L. So you have to calculate the magnitude of flux passing through the square. So options are 2b naught L square Weber, 3b naught L square Weber, 4b naught L square Weber, or root 29b naught L square Weber. So I will give you some time to solve it. Okay, let's see the solution. So correct option is C, 4b naught L square Weber. So what are given things? Magnetic field is given B equal to B naught 2I cap plus 3j cap plus 4k cap Tesla. Area is given naught. Square of side L is given. We know that area of the square is A equal to L square, side square. So side of square is given L meters. So area will be L square. Since square loop is lying in XY plane, so we know that area vector is perpendicular to the surface of the, or we can say plane of the square loop or any loop. So square loop is in XY plane, so area vector will be in Z axis. So area vector will be directed towards Z axis. That is, now this is the notation for area vector. So A vector, this is area vector, which is equal to L square. L square is the magnitude of area and K cap is the unit, direction. This is unit vector representing the direction of area vector. So area vector is directed towards Z axis. So direction of this area vector is towards Z axis and it is represented by unit vector K cap. Okay. The magnetic flux linked with the uniform surface area and uniform magnetic field is given by phi b is equal to b dot a. So according to NCERT equation 6.1. So b, this is b vector dot a vector. This is cross product of magnetic field and area vector. Magnetic flux formula. Okay, so magnetic flux is equal to, so put the value of magnetic field, which is equal to b naught 2i cap plus 3j cap plus 4k cap dot, what is the value of area vector? L square k cap. So now we will do the dot product of both these quantities. So b naught L square is a constant, so they will we will write there in the beginning of the equation. So b naught L square, they are constant, they will not participate in the dot product. So in dot product there is 2i cap plus 3j cap plus 4k cap dot k cap. Now we know that how we can calculate the dot product after multiplying the coefficients of similar unit vector. So in that place there is no I cap, in the area vector there is no I cap, there is no j cap. Okay, so coefficient of I cap and j cap in the area vector, direction of area vector, will be 0. So we are going to multiply the coefficients. Okay, this is the way we are going to calculate the dot product. Okay, when we are taking the dot product, we are going to multiply, this is the method, we are going to multiply the coefficients of the similar unit vectors. So in the direction of area vector, the coefficient of I vector and j vector is 0. So multiply 2 with 0, multiplying 3 with 0, and multiplying 4 with the coefficient of k cap. And in the direction of area vector, the coefficient of k cap is 1. So 4 into 1. So after simplifying it, 2 multiplied by 0 plus 4. So it will result in 4 b naught L square. So phi b will be equal to 4 b naught L square Weber. Okay, so this is the method of, so this is 1. This is 1 is the coefficient of this k cap. We are taking dot product. Okay, so direction of this area vector is 0 I cap plus 0 j cap plus k cap. So if there is no coefficient of k cap, it means the coefficient is 1. If there is nothing written with the k cap or any unit vector, it means it is 1. So coefficient of k cap here is 1. Okay, so coefficient of I cap and j cap is 0 in the direction of area vector. So taking dot product, it will result in 4. Okay, so phi b equal to 4 b naught L square Weber. So option C is correct option. Now next question, NCERT Exemplar 6.2. Question: a loop made of straight edges has 6 corners. There is a loop of 6 corners at, now there are the coordinates of all the corners. A corner coordinates are 0, 0, 0. So this loop is placed in 3D. That's why we are taking all 3 coordinates: x coordinate, y coordinate, z coordinate. Okay, so A coordinate. So A corner is placed at 0, 0, 0, means at origin. B corner is placed at L, 0, 0. Y is 0, Z is 0, L, means B corner is in the at the x-axis at a distance L from the origin. C corner L, L, 0. It is placed in xy plane. D corner is 0, L, 0. It is placed in on y-axis. E corner is 0, L, L. It is placed on YZ axis. And F is equal to 0, 0, L. So this F corner is placed at Z axis. A magnetic field B equal to B naught I plus K cap. So magnetic field is existing in the which plane? This is the coefficient of, this is the unit vector of x axis. K cap is the unit vector of Z axis. There is no unit vector of y axis. So magnetic field is exist in which region? In the xz plane. So B equal to B naught I cap plus K cap Tesla is present in the region. The flux passing through the loop A, B, C, D, E, F, A. This is the whole loop. In that order is. So we have to calculate the flux passing through the loop. So corners of the loop are given. Okay, magnetic field value is given. So you have to find the magnetic flux through the coil. So options are B naught L square Weber, 2 B naught L square Weber, root 2 B naught L square Weber, and 4 B naught L square Weber. So these type of questions are important type questions. Okay, when loop is placed in 3D and magnetic field is also given in the space, you have to calculate the magnetic flux passing through that. Okay, so I will give you some time to solve it. Let's see the solution. So correct option is B, 2 B naught L square Weber. So what is given? B equal to B naught I cap plus K cap Tesla. This is given. A loop with 6 corners is shown in the figure. So diagrammatic representation of this loop is given as like this. So this is x-axis, y-axis, z-axis. So A corner is at origin, B is at x-axis, C is at xy plane, and D is at y-axis, E is in yz plane, and F is at z-axis. Okay, so this is the orientation of the loop in the 3D space. Okay, so figure showing the loop has two surfaces. So if we divide the surface of the loop in two parts, so one part is A, B, C, D, second part is A, D, E, F. Okay, there are two parts of the loop. Okay, so area vector for both these loops will be different also. For surface A, B, C, D, for this surface which is placed in XY plane. So surface ABCD lies in XY plane. Its area vector points normal to the surface. So it is placed in XY plane. So its area vector will be in towards Z axis. So it is along Z axis. Area vector of this surface ABCD. Area vector of ABCD will be equal to, we can write the area of this ABCD as A1 and area of this ADEF as A2, and combined area of this loop will be A. Okay, so A1 will be equal to, so you can see that length of this side AB, B is placed at L distance from the origin, so length of this side is L. Okay, and C is placed at L distance from origin in the direction of x-axis. X coordinate is L, y coordinate is also L. That means it is square. This loop ADEF is also square. So length of the side is given L. So area will be L square. Magnitude of area will be L square. And area vector will be A1 equal to L square. What is the direction of area vector for this ABCD? K cap. Okay. So this is the A1. Now we will find the A2 for another surface. Now for surface ADEF. Surface ADEF lies in YZ plane. So it is lying in YZ plane. So area vector will be towards x-axis. So area vector points normal to the surface, that is along x-axis. So area vector of ADEF, so A2 will be equal to, again length of side for this loop is also L. So area will be L square again, but the direction of area vector will be different in this case. So direction of area vector will be towards x-axis and unit vector will be I cap, like this. So A2 will be equal to L square I cap. Now we will combine the areas for both the surfaces for entire loop. So resultant area vector will be equal to A equal to A1 plus A2 will be equal to L square K cap plus L square I cap. Okay, so we cannot add the area due to both surfaces directly by ordinary algebra. Okay, we are adding up with the vector algebra. So that's why we have not added up L square plus L square. We have not written 2L square. Okay, so we have marked the direction also. L square K cap plus L square I cap. So these both terms cannot be added by ordinary algebra. These two terms can be added with the help of vector algebra only. Okay, so we will write A equal to L square. We can write it as, we can take L square common, but direction will be I cap plus K cap. We cannot add up the direction. So I cap plus K cap will remain as it is. So this is the vector algebra. Now B is in, you can see the magnetic field B equal to B naught I cap plus K cap. Area vector is also A equal to L square I cap plus K cap. Okay, now both are in the same direction, I cap plus K cap. Both magnetic field and area vector is in the same direction. So there will be magnetic flux, and that is maximum magnetic flux linked with the coil. Okay, so magnetic flux linked with the uniform surface of area A in the uniform magnetic field is given by phi B is equal to B vector dot A vector according to NCERT equation 6.1. So substituting values of B vector and A vector. So phi B will be equal to, what is B? B naught I cap plus K cap dot L square K cap plus L square I cap. So taking common L square, we will left with phi B equal to B naught L square. Now you have to take dot product. So L square is taken as common. So I cap plus K cap dot I cap plus K cap. Okay, so B naught L square I cap dot K cap, this term, like we do A plus B into A plus B. Okay, the formula, that algebra, A plus B into A plus B. We multiply A with A, then A with B. Okay, plus B with A plus B with B. Like that. You have to multiply this I cap with that K cap plus this I cap with this I cap plus taking dot product of this K cap. Now we are not multiplying, we are taking dot product. So taking dot product of K cap with this K cap plus, and again taking K cap dot I cap. Okay, so phi B, that B naught L square will be with the all the terms. It will they are coefficient, they will remain with all the terms. So B naught L square I cap dot K cap, first term, plus B naught L square I cap dot I cap, second term, plus B naught K cap dot, sorry, B naught L square K cap dot K cap, third term, plus B naught L square K cap dot I cap. So these are the four terms. Okay, mark it as first equation. Now dot product of orthogonal, or we can say perpendicular vectors, is also zero, always zero. So therefore I cap dot K cap and K cap dot I cap is equal to 0, because I cap is in the x direction, K cap is in the z direction. So angle between both this unit vector is 90 degree. Okay, so they are orthogonal, or we can say perpendicular vectors. So their resultant will be magnitude of I cap, magnitude of K cap, and cos theta, and theta is 90 degree. Okay, so cos 90 degree is 0. So dot product of two vectors that are perpendicular is equal to 0. So both these terms, I dot K cap and K cap dot I cap, will become 0. Okay, so these two terms will get cancel out from the equation 1. Also I cap dot I cap. So the dot product of the same vector with itself, and k cap dot k cap, it will result in magnitude of I cap. Since I cap is unit vector, so magnitude of this unit vector, magnitude of unit vector is unity 1. So magnitude of this I vector, magnitude of this another I vector, both magnitude of both these unit vector will be 1. That's why they are called unit vectors. And angle between them, they are along the x-axis. Both are along the x-axis. So angle between both these are 0 degree. So cos 0 degree is also 1. So if two same unit vectors are in dot product, the result will be 1. Okay. So after putting all this value in equation 1, so equation 1 gives phi b equal to, so I dot k cap and k dot I cap, these term become 0. So 0 plus, and these two terms I dot I and k dot k, this will result in 1 1. So it will result in b naught L square plus b naught L square plus 0 again for this. Okay, so phi b will be equal to 2 b naught L square Weber. So this is the final answer. Got it? So which option is correct? Option B is correct option. Okay, so you have to learn all the properties of the dot products. Okay, so you will need the dot product and cross product in the further topics also. So you have to learn all these properties also. Okay, so this method is somewhat long, but it is more reliable than finding the magnetic flux with other method also. By cos theta, BA cos theta, you can find by that method also if you feel like that method is easy to implement or that method is short. Okay, but this method is more reliable to solve it. Okay. Okay, next question. The self-inductance L of a solenoid of length L and area of cross-section A with a fixed number of turns N as. So this self-inductance L, we know the formula for L, which is equal to mu naught N square AL. Okay, for a solenoid. So this self-inductance L of a solenoid of length L and area of cross-section A with a fixed number of turns N. So fixed number of turns N is given, not fixed number of turns per unit length. So you have to convert this formula in the terms of number of turns, capital N. Okay, increases as. So this self-inductance will increase when? Options are when L and A both increases, when L decreases and A increases, when L increases and A decreases, when both L and A decreases. So I will give you some time to think about it. So let's see the solution. So correct option is B, when L decreases and A increases. So what is the thinking process for this question? The self-inductance L of a solenoid depends on its geometry, that is length, cross-sectional area, number of turns, etc., and on the permeability of the medium. Okay, so self-inductance of a long solenoid having cross-sectional area A and length L n turns per unit length and a material of relative permeability inside the core is given by L equal to mu r mu naught n square Al. So when there is no material inside the core, then you can write mu naught n square Al. When there is a material core inside the solenoid, then it will be written as mu r into mu naught n square Al, and this mu r into mu naught will become mu. That is the permeability of the medium. So NCERT question 6.16. Now they have given in the question that fixed number of turns n. We have to find the proportionality of the self-inductance L with the area and length only. But here for small n, there is capital N upon L. L is appearing in the small n also. So we cannot assume that small n is also fixed or constant. Small n can vary. Okay, because length can vary. Only number of turns is fixed, capital N. So we have to convert this formula in the terms of capital N. So L is equal to, self-inductance is equal to mu r mu naught n square, capital N square A upon L, by putting small n equal to n by L. So there was small n square. So it will result in capital N square upon L square. And L was in the numerator also. So 1L in the numerator will cancel out with the 1L with the denominator. So it will result in mu r mu naught capital N square A by L. Now relative permeability of medium is fixed, mu naught is fixed, constant, and N is also fixed given in the question. So L is proportional to, now L is proportional to area upon length, because all other things are constant now. So L is proportional to, self-inductance is proportional to area upon length. Therefore self-inductance L will increase with increase in area A, and it will decrease, it will increase also with the decrease in length L of the solenoid. So it will increase when area will increase and length will decrease. Okay, so you have to convert or modify the formula according to the question. So what is given in the question? If there was fixed number of turns per unit length small n, then self-inductance will be directly proportional to AL. But in the question it is written fixed number of turns only, capital N. So you have to convert the formula in the terms of capital N. Then you can apply the proportionality. Okay. So option B is correct. Note, the capacitance, resistance, self and mutual inductance depends on the geometry of the devices as well as the permittivity or permeability of the medium. Permittivity in the case of capacitance. Okay, and permeability in the case of self and mutual inductance. Resistance, there is no permittivity or permeability. Okay, but resistance also depends on the geometry of the conductor. Capacitance also depend on the geometry of the device, and self and mutual inductance also depends on the geometry of the solenoid or coil. Got it? So next question, NCERT Exemplar 6.8. An EMF is produced in a coil which is not connected to an external voltage source. This can be due to the coil being in a time varying magnetic field. So what are the conditions to induce the EMF in the coil? So it is not connected to external voltage source. So EMF is induced. How? This can be due to the coil being in a time varying magnetic field, or the coil moving in a time varying magnetic field, the coil moving in a constant magnetic field, the coil is stationary in external spatial varying magnetic field which does not change with time. So in the last option there is magnetic field which is not varying with time, but it is varying spatially. That means it is varying with the position. If we are here, magnetic field will be having some value. If we are moving from one point to another point, magnetic field will change. It doesn't depend on time, but depend on space, depend on the position. So spatially varying magnetic field. Okay, so coil is stationary in the external spatially varying magnetic field which does not change with time. So which of the options are correct? So this is the type of question, this is a type of MCQ where more than one option can be correct. Okay, so I will give you some time to think about it. So option A, B and C, these are correct options. So let's see, thinking process. This problem is associated with the phenomenon of electromagnetic induction. That means, according to Faraday's law, EMF is produced in the coil when magnetic flux linked with it changes with respect to time. Okay, so how we can change the magnetic flux? By changing the magnetic field, by changing the area which is in the magnetic field, and by changing the orientation of the coil. Okay, so magnetic flux through the coil of area A placed in the magnetic field B is given by phi B equal to BA cos theta. So magnetic flux through the coil can be changed by changing magnetic field with time, changing area of the coil, or changing orientation of the coil with respect to magnetic field. So by these three things, that means by changing B, A and theta, we can change the magnetic flux through the coil and we can generate the EMF. We can induce the EMF in the coil. So therefore magnetic flux linked with the isolated coil change when the coil being in the time varying magnetic field. If magnetic field is varying with time, coil is stationary but magnetic field is varying with the time. So since the magnetic field lines are varying, or magnetic field through the coil is varying with time, even if the coil is stationary, magnetic flux is changing through the coil, due to which EMF will be induced. So this is the first method. Second method, coil is moving in a constant magnetic field. So coil is moving. So due to the motional EMF, EMF will be induced. We have discussed the topic of motional EMF. So this coil is moving with constant velocity in the constant magnetic field. So EMF will be induced. And third case is the coil moving in the time varying magnetic field. Even if coil is stationary in the time varying magnetic field, EMF will be induced. And if coil is moving in the time varying magnetic field, then also EMF will be induced. Okay, so option D is incorrect. Why? So option D is incorrect because electromagnetic induction requires a change in magnetic flux to produce an EMF. And since the magnetic field is not changing with time, no EMF will be induced in the coil. So what was the D option? It was given that spatially varying magnetic field. That means magnetic field is varying from position to position. Magnetic field is not varying with respect to time. So coil is stationary, placed in spatially varying magnetic field. So coil is stationary, so magnetic field through it, or we can say magnetic flux through it, will be constant if it is not changing positions. Okay, so there is no EMF. No EMF will be induced in the coil if the coil is stationary. If coil is moving, then there will be change in the magnetic flux and EMF will be induced. Okay, so that is spatially varying magnetic field. So next question, consider a magnet surrounded by a wire with an on-off switch S, figure 6.4. If the switch is thrown from the off position, that is open circuit, like given in the first diagram, circuit is open and it is thrown from the off position, that is open circuit, to the on position, that is in the second figure, closed circuit. That means we are closing the circuit. Will a current flow in the circuit? This magnet is not moving. Okay, this wire is surrounding the magnet. Initial condition, circuit is open, key is open. Okay, so when we tap the key or we will close the circuit, we will there will be a on position, that means closed circuit. Okay, will there be EMF will be induced in this coil or current flow in the circuit. Okay, so if there will be a EMF or current, explain why. And if there will not be any current or EMF induced in the circuit, then explain that thing also. Okay, so I will give you some time to think about it. So let's see the solution. So magnetic flux linked with the uniform surface of area A in uniform magnetic field B is given by. So magnetic flux is given by B vector dot A vector, which is equal to BA cos theta. Okay, so either magnetic field can change, should change, or either area should change, or either orientation should change to change the magnetic flux according to NCERT equation 6.1. So flux linked with the coil will change only when either B or A or the angle theta between the B and A change. Okay, bar magnet is stationary. There is no relative motion between the bar magnet and the coil. That means magnetic field through the coil is not changing. Bar magnet is stationary, so magnetic field through the coil with respect to time is not changing. So it will be constant. Here also area and orientation of the coil is unchanged. Area of the coil is not changed and orientation of the coil is also not changed. Okay, so that means nothing is being changed. So therefore when the switch is thrown from the off position, that is open circuit, to the on position, closed circuit, then neither B nor A nor the angle theta between B and A change. Okay, if there will be a relative motion, if there would be a relative motion between bar magnet and coil, then there will be change in the magnetic flux and EMF will be induced. Area we are not changing and orientation of the coil we are not changing. Okay, only possibility is when bar magnet would be in the relative motion with respect to the coil, then there will be flux change. But bar magnet is also stationary. Therefore neither B nor A and nor the angle theta is changing. So does no change in the magnetic flux linked with the coil occurs. Hence no electromagnetic force, that is EMF, is produced and consequently no current will flow in the circuit according to Faraday law of electromagnetic induction. If there is no change in the flux with respect to time, then there will be no EMF induced, then there will be no current flowing through the circuit even if we close the circuit. Okay, so what is the condition for EMF induction? Change in magnetic flux. Okay, and for change in magnetic flux, magnetic field, area or orientation should, one of these things should change. Okay, so next exemplar, NCERT Exemplar 6.13. A solenoid is connected to a battery so that a steady current flows through it. if an iron core is inserted into the solenoid, will the current increase or decrease? Okay, so we are inserting an iron core inside the solenoid. So what will be the consequences? What will happen after that when we insert iron core inside the solenoid? Magnetic field will increase or decrease? Okay, due to which magnetic flux increase or decrease or remains constant? Okay, that thing you have to think. Will the current increase or decrease? Explain. So I will give you some time to think about it. So your thinking process, you have to think that what is the effect of iron core on the magnetic field, and what is the effect of magnetic field on the magnetic flux, and what is the result of change in magnetic flux. Okay, so let's see the solution. So figure showing pattern of magnetic field lines around the solenoid. So there is a solenoid, current is flowing through it, and iron core is inserted inside the solenoid. So these are the magnetic field lines. So when we place any iron core, we have discussed it in magnetism and matter. So there will be magnetization of the iron core, due to which total magnetic field will increase. Okay, so here the application of Lenz's law is tested through this problem. So when the iron core is inserted in the current carrying solenoid, the total magnetic field increases due to magnetization of iron core. Okay, due to the magnetization of iron core, it will be having its own magnetic field, which will be in the same direction as the magnetic field of solenoid. So it will increase the total magnetic field through the solenoid due to the magnetization in the same direction. Soft iron core or iron core is ferromagnetic material. So it will be magnetized in the same direction of the magnetizing magnetic intensity of the solenoid. Okay, so total magnetic field will increase. So total magnetic field increase due to the magnetization of the iron core. Therefore, magnetic flux linked with the solenoid also increases. If magnetic field through the solenoid is increasing, so magnetic flux linked with the solenoid will also increase. Means there is a change of magnetic flux. So according to Lenz's law, the EMF current induced must oppose this increase in flux. So according to Lenz's law, that EMF will be induced in the coil or solenoid, that will be in such a way that will oppose the increase in the flux, which can be done by making decrease in the current. Okay, so how can a solenoid, how can a EMF that is induced in the solenoid can reduce the magnetic flux or can oppose the increase in flux? By inducing the EMF in the opposite direction of the existing current, due to which current will decrease in the circuit and magnetic field will also decrease. Magnetic field is increasing, so it has to oppose the increasing magnetic field. So current will be induced in the opposite direction of the existing current in the solenoid, and hence the total current will decrease. Okay, so the additional magnetic field that is produced due to the iron core, we have to neutralize that effect, and we have to maintain the same amount of magnetic field in the solenoid. So it will be done by the EMF induced. So this EMF will be, or we can say current will be induced in the opposite direction of the existing current. Okay, therefore total current will decrease and magnetic field will also decrease. Okay. Next question. A long solenoid S has n turns per meter with diameter A. At the center of this coil, we place a smaller coil of n turns and diameter B, where B is less than A. Smaller coil is being inserted in the larger solenoid. Okay, and long solenoid is having diameter A and smaller solenoid is having n number of turns and diameter B, where B is less than A. If the current in the solenoid increases linearly, if current in the outer solenoid, which means long solenoid, is increasing linearly with time, so current is not steady here, current is varying with time. So what is the induced EMF appearing in the smaller coil? We have to find the induced EMF in the smaller coil. Plot graph showing nature of variation in the EMF if current varies as a function of mt square plus c. Okay, so current varies as a function of mt square plus c. So now you have to plot the graph of the variation in the EMF. Okay, so let's see. So firstly we have to derive the expression for this till this part, that current is linearly varying with time and what is the induced EMF appearing in the smaller coil. Firstly we have to derive the expression till that part. Then we have to plot the graph of the EMF with respect to time when current will be varying according to mt square plus c. This c is a constant, m is also constant, this t square. Okay, so let's see. So I will give you some time to think about it. So let's see the solution. So what is the thinking process for this question? This problem requires an insight to magnetic field due to current carrying solenoid having varying current, which induces EMF in relatively smaller coil placed at the center of the solenoid. Okay, so let I be the current flowing through the solenoid that is varying linearly with time. Now magnetic field due to the solenoid S will be equal to B naught, B equal to mu naught Ni. So this is the magnetic field inside the solenoid. We have derived this relation before. Okay, so I is the time varying current. So magnetic field will also be time varying. So magnetic flux through smaller coil will be phi b equal to n into n is the number of turns of the coil into b into a. B is the magnetic field produced by the larger solenoid. Okay, A is the area of the smaller solenoid, smaller coil, and n is the number of turns of smaller coil also. Okay, where A is equal to pi b square. So that A is the area of cross section of the smaller coil of n turns. Magnetic field is produced by the long solenoid, not by the smaller coil, because current is flowing in the long solenoid. So applying Faraday's law of electromagnetic induction, EMF induced in the smaller coil is equal to epsilon equal to minus d phi by dt. So what is phi we have calculated is equal to NBA for the, so magnetic flux through the smaller coil phi is equal to NBA. So minus d by dt, phi is equal to NBA. So epsilon equal to minus n. What was n? Number of turns. So it is fixed. It will come out of derivative. What is a? Pi b square. It is also constant. It will come out of the derivative. So in derivative it will be only b, because b is varying, magnetic field is varying, because current is varying with time. So magnetic field is mu naught n I. So I is varying, that's why b is varying. So b will be in the derivative. So where b is equal to mu naught ni, so we'll put this. So epsilon equal to minus n. So number of turns per meter is also constant. For long solenoid, mu naught is also constant. So mu naught n will come out of the derivative, only current will remain in the derivative. So minus n pi b square mu naught n di by dt. So this is the expression. This is the expression till this part of the question. That is that thing is asked, that if the current in the solenoid increases linearly with time, what is the induced EMF appearing in the solenoid smaller coil? So this is the EMF induced in the smaller coil. Now other part of the question is, if current varies as a function of mt square plus c, then plot a graph of showing nature of variation in the EMF. So b here is diameter of the smaller coil. So pi b square is the area of the smaller coil, area of cross section. Since current varies as a function of mt square plus c, so current varies as a function of mt square plus c, so put mt square plus c in the place of I. So epsilon equal to minus n pi mu naught b square, and in the place of I we are placing mt square plus c. So differentiate mt square plus c with respect to t. So that m will come out of the derivative, and t square will be 2m. T square derivative of t square with respect to t will be 2t. So 2mt plus c. C is constant. So differentiation of constant will be 0. So 2mt plus 0. So it will result only 2mt. So mu minus mu naught capital N small n pi b square 2mt. So this is the entire expression for the EMF. So EMF will be equal to mu naught capital N small n pi b square 2mt. Okay, so this is the expression for EMF. The magnitude of EMF varies with time as shown in the figure below. So this is the plot. So magnitude of EMF. So magnitude of EMF is varying, is directly proportional to T. Only magnitude. And this negative sign is representing the polarity of the EMF. Okay, so we are plotting a graph with magnitude of EMF and T. So this mu naught is constant, capital N is constant, small n is constant, pi is constant, b square is constant, 2 is constant, and m is also constant. So this EMF is directly proportional to T, or we can say magnitude of EMF is directly proportional to T. So the graph will be linear. Okay. So thank you. This is all about today's lecture, NCERT Exemplar.